Welcome to our Quantum Deep Dive. Today, we're exploring the work of a true pioneer, David Wineland, who you could really call a central architect of what's now known as the second quantum revolution.
And our guide for this journey is an absolutely insightful essay by Georg Owa Schneeppot. Okay, let's dive right in.
At its heart, Wineland's entire career is about this one fundamental shift, taking quantum mechanics from this, kind of weird theory on a blackboard and turning it into a powerful tool that we can actually build things with. He helped make the strange, spooky rules of the quantum world into an engineering discipline. And to really get why Wineland is such a big deal, you have to understand this transition. The first quantum revolution, think Einstein and Bohr, gave us the rules of the quantum game. The second revolution, which Wineland helps kickstart, is all about becoming master players, actively controlling and manipulating individual quantum systems to do our bidding. So we're going to follow Wineland's incredible journey through 5 key stages, from the big ideas that drove him to the actual tools he built, and finally to the lasting impact he's had on the technology of tomorrow. So what does it actually mean to control the quantum world? I mean, it sounds like science fiction, right? Well, it's the ultimate act of micromanipulation. It means isolating a single particle, like an ion, holding it perfectly still, and making it do exactly what you want it to do. But to get that kind of control, a pioneer needs some serious tools. And for Wineland, these weren't just physical gadgets, they were concepts and techniques that he forged during his PhD at Harvard, studying under the Nobel laureate Norman F. Ramsey. Yeah, his mentor, Norman Ramsey, was a huge influence. See, Ramsey's work planted this really revolutionary idea in Wineland's head. Don't just measure quantum systems from the outside, but instead use them as the instruments themselves. That philosophical shift was the key, and it led Wineland to focus on the insane challenge of trapping and controlling a single particle. Okay, so the first tool you need is an ion trap. The best way to think of it is like a set of invisible electromagnetic tweezers. By using these oscillating electric fields, Wineland's team could grab a single charged atom and just hold it there, perfectly still, totally isolated from the noisy outside world for hours on end. But even a trapped ion still jiggles around like crazy because of heat. So how do you get it to stop moving? That's where the absolute genius of laser cooling comes in. You tune a laser to a frequency just a tiny bit below what the ion naturally wants to absorb. Now, because of the Doppler effect, the ion only absorbs a photon when it's moving towards the laser, which gives it a tiny push, slowing it down. It's literally like stopping a speeding car by throwing perfectly timed ping pong balls at it. And this 4-step process, which Wineland really perfected, was a complete game changer. I mean, for the very first time in history, a physical object was brought to its quantum ground state of motion. It was perfectly still, with only that tiny bit of zero-point energy that quantum mechanics says it has to have. It was a clean, stable slate, just sitting there, ready to be manipulated. Okay, so Wineland has a trapped, cooled ion. That by itself is an incredible physics achievement. But what his team at the National Institute of Standards and Technology, or NIST, did next, well, that's what really kicked off the entire era of quantum computing. And, this didn't happen overnight. As you can see from this timeline, it was the result of almost 2 decades of incredibly painstaking experimental work. From those first papers on cooling way back in '78 to figuring out how to build traps that could hold a whole line of ions, every single step was building towards this one landmark moment in 1995. This right here was the hello world moment for ion trap quantum computing. The title of their 1995 paper is so incredibly understated, but its impact was just monumental. They didn't just create a quantum bit, a qubit. They actually made it perform a logical operation. And that's the absolute foundation of any computer. So here's the core idea. They used 2 energy levels inside a single beryllium ion to represent a qubit, the quantum version of a 0 or a 1. With lasers, they could put this qubit into a superposition, which just means it's both a 0 and a 1 at the exact same time. But the real breakthrough was creating something called a CNOT gate. This let them use one ion to flip the state of a second ion, proving for the first time that these totally bizarre quantum effects could be engineered into the basic building blocks of a computer. Now, this unbelievable level of control over single atoms had another revolutionary application. One that affects something many of us just take for granted every single day, telling time. Right. Wineland realized that the vibrations of an electron inside a single laser-cooled ion are by far the most stable and high-frequency oscillators that have ever been created. The tick of this clock is an electron jumping between energy levels, and it's incredibly consistent. This was the key to building what we now call optical atomic clocks. So, using ions like aluminum-27, his team at NIST built clocks with a truly mind-boggling level of precision. Their inaccuracy was less than 1 part in a quintillion. That is a 1 followed by 18 zeros. It's just an insane number. Yeah, it's a number that's so big, it's almost impossible to imagine. It just feels abstract. So what does that level of accuracy actually mean in the real world? It's almost unbelievable, isn't it? A clock this precise is so sensitive it can actually measure the effects of Einstein's general relativity. You know, the idea that time literally ticks slower in a stronger gravitational field. If you lift one of these clocks up by just a few centimeters, you can measure the slowing of time itself. Wow. And this is not just some academic exercise. This level of precision has really profound implications. It makes GPS better, it lets us map Earth's gravity field to monitor things like groundwater levels, it synchronizes our global data networks, and it even lets physicists test whether the fundamental laws of the universe are actually changing over time. So in 2012, this incredible body of work, spanning both quantum computing and precision timekeeping, was finally recognized with the highest honor in all of science. He shared the Nobel Prize with Serge Haroche from France, who had accomplished similar feats but using a totally different system, with photons. And the Nobel Committee's citation here is so important. They specifically honored their ability not just to see or measure the quantum world, but to actively manipulate and control it. But after he retired from NEST, Wineland continued his work at the University of Oregon, and he focused heavily on mentoring the next generation, because as profound as his own discoveries were, his influence extends so much further than his own papers and prizes. So many of his former students and postdocs are now the leaders in the quantum field. Christopher Monroe went on to co-found IonQ, which is a leading public quantum computing company. Others are running world-class labs from the US to Germany, all pushing the boundaries of what's possible. And really, the people listed here are just a tiny fraction of those he's influenced. The impact is just undeniable. His methods have become a global standard. The technology that was born in his lab at NIST now forms the backbone of commercial and academic quantum efforts all over the world, from companies like IonQ to major university hubs in Europe. He didn't just make a discovery. He created an entire platform that a whole industry is now building on top of. He really did. He built the bridge from fundamental theory to applied technology. He transformed quantum mechanics from a descriptive science into an engineering discipline. And in doing that, he paved the way for the quantum age. The question is no longer if we can control the quantum world, but what on earth are we going to do with all that control? And that's our look into the incredible, pioneering work of David Wineland, based on that fantastic essay by Jörg O. Schneeppot.
To explore the original source material for yourself, please visit schneeppot.de. Goodbye for now.
Schneeppot.de is a private project by Jörg O. Schneeppot dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.